You might have come across situations where you need to send some critical data between two parties, and ensuring its security is a top priority. You decide to send encrypted data, but how do you ensure the data has not been tampered in transit? This is referred to as integrity of the data. Data integrity refers to the fact that the data remains accurate, unaltered, and consistent throughout its life cycle. And integrity of digital data is accomplished using hashing algorithms. Our goal over here is to check the integrity of the message. In other words, we want to ascertain that the message has not been tampered in transit. And a very shallow explanation of what we'll be doing in the next few sections is this. We'll run a hash function against a given message, say M. We'll send this message over to Bob, the receiver, and we'll run the hash function again at Bob's end to verify if the received hash and the freshly generated hash are the same. The table that you see here is called an oracle table. The columns on the left is the plain text, and the columns on the right is the hash for this given plain text. In fact, the hashes that you see here are generated using SHA-256 for this plain text. What I want you to notice is the fact that any hashing algorithms can take n bits of input and map it to exactly m bits of output every time. For SHA-256, it can take arbitrary long bits of input and map it to 256 bits of output, or 32 bytes of output. Now it's time for you to understand what MDC means. Suppose Alice wants to send some critical data over to Bob. If Eve manages to intercept this message, they may modify it. It is important to understand that we are talking about the integrity of the data and not the confidentiality of the data. Say, even after Alice encrypts this message and sends this encrypted message over to Bob, it doesn't inherently guarantee that the data hasn't been tampered in transit. Even though Eve may be unable to decrypt this encrypted message, they may modify this, the ciphertext in transit. This could involve arranging, altering bits, or rearranging packets, or injecting malicious code, which could all lead to potentially unwanted consequences upon decryption. This is where an MDC comes in. It goes by many names: a message digest, a checksum, or sometimes referred to as the hash of a message, something that the hash function generates. Note that this hash function could be anything, say a SHA-256 or MD5 or CRC. Once the digest is generated, it serves as a unique fingerprint for the original message. When Alice wants to send this message and its corresponding digest over to Bob, Bob can independently apply the same hash function at their end and generate their own corresponding digest, or the MDC. If the calculated digest matches the one that is received from Alice, it serves as an irrefutable evidence that the data hasn't undergone any modifications during transition. A notable point over here is that the message is transferred over an insecure channel, but the MDC necessarily has to be transferred over a channel that is immune to change, or a trusted party. But what happens if the trusted party itself is compromised? Well, in such a case, Eve can intercept this message M, modify it, and let's call this modified message M dash. Now Eve can generate their own digest against this message. Let's call that MDC dash and forward this M dash and MDC dash over to Bob. Now Bob will receive M dash and MDC dash. And now when Bob uses the same hash function to generate their own digest, they'll get this MDC dash. Bob will have no way to verify if the data originated from Alice or Eve. What MDC lacks is a definitive guarantee of the message origin, leaving a potential vulnerability in confirming the true sender. This is where a message authentication code or a MAC comes in. MACs not only ensure the integrity of the message, detecting any unauthorized altercations, but also provide a mechanism for authenticating the origin of the data. In other words, MAC offer an assurance that the message is indeed originating from Alice and not by someone else. A MAC consists of a pair of signing algorithm S and a verification algorithm V. The signing algorithm takes in the message M along with a secret key K to generate a valid MAC. The verification algorithm, which is used by Bob, takes in the message M, the same secret key K, and the received MAC to verify if the message is consistent. Since Eve does not have this secret key K, they cannot modify the message to generate a valid MAC. While MACs may look secure, it's vulnerable to a class of attacks known as the length extension attacks. Say at this point, Eve intercepts the message. What they know is the message M and the MAC, which was generated using the hash algorithm. Mathematically, we'll say that given the hash of a message, which was generated using the key K and concatenated with the message M and the message M, Eve can extend this M to M dash. Mathematically, this M dash will be defined as the message M concat a pad, concat the malicious word that Eve chose. Eve will now create a MAC for this M dash, which is basically using the signing algorithm or the hash function, which takes as parameter the key K concat the new M dash, which is M concat the pad concat the malicious word W. And this is done by supplying the hash algorithm an initial running state of the MAC that we just received, of the hash that we just received. Now, when Bob receives this modified message M and the corresponding MAC of M dash, they are unable to determine this modification. This is where HMACs or hashed-based MACs fell in. HMAC is a specific construct for generating a MAC algorithm out of collision-resistant hash functions. They use two passes of hash computation and provide better immunity against length extension attacks. Let's see how it's done. The message M is first divided into n blocks, each of b bits. We'll then select a secret key K and XOR it with a constant I called iPad or the input pad. We'll have to ensure that this key is of K bits, so we left pad it with 0 just to be sure that it's of B bits. And then we'll prepend this freshly generated block in this message to create n plus 1 blocks. We'll then pass this n plus 1 block to the hash algorithm and generate an n-bit HMAC called an intermediate HMAC. Now, we'll prepend this HMAC with zeros just to be sure that it's of b bits. And this is the first block, or the second block rather, that we'll be using in the next pass. But the first block that we'll need in the next pass comes from another XOR operation where we'll necessarily need the key k. We'll again left pad it with zeros just to be sure that it's of b bits, and again XOR it, this time with another constant called the opad or the output pad. We'll pass this block as we'll prepend this in the HMAC block and pass this in the second pass to generate an n-bit final HMAC. Mathematically, the signing algorithm can be represented as, given the key k and the message m, compute the hash of k XOR opad concat with the hash of k XOR ipad concat with the message. Now, let's see what Eve can intercept in this case. At this point, Eve may know the HMAC and the message M. Note that these ipad and the opad are well-known constructs defined in the constants defined in the HMAC construction. And Eve definitely knows that. So Eve is aware of those special constants. We'll come to that in just a bit. So now let's try to perform an length extension attack in this construct. Let's say Eve adds a few malicious blocks over here, and then uses the same hash function to somehow compute the intermediate hash, the HMAC. They'll use this as a second block in the second pass. But to compute the first block, they'll necessarily have to know the key. And since Eve does not know the key, they cannot add the first block, they cannot prepend this with the HMAC, and thus they cannot pass the second pass. They cannot compute the second pass. Well, that's just the beginning of all problems for Eve. Remember that we computed HMAC at this point, right? So to compute the intermediate HMAC fast, we need to provide the running state. We'll need to provide the HMAC at this point as a running state for this hash function. And since we intercepted the HMAC at this point, which is the running state for this HMAC, it is very difficult for Eve to even generate this intermediate HMAC. Mathematically, we'll say that the hash of opad XOR key k and the, again, concat with ipad, hash of ipad, concat message, concat a pad, just to be sure it's of b bits, with a malicious word w. Even if Eve is able to compute this, they will not be able to know the key, the secret key k, and thus they'll not be able to pass the second pass. They'll not be able to compute the second pass rather. This is how this HMAC provides a better immunity against length extension attacks. Now let's talk about this special construct, the special constants defined in the HMAC standards, the ipad and the opad. Well, the value of ipad is taken as b over 8 repetitions of the sequence 0, 0, 1, 1, 0, 1, 1, 0, which is again 36 for hex. And the output and the value for this OPAD is taken as b over 8 repetitions of the value 0, 1, 0, 1, 1, 1, 0, 0, which is 5C in hex. Now, note that these values are such taken that the Hamming distance between them is most non-regular. And what I mean by Hamming distance in such a case is that the difference between the bits of these sequences. So the different number of bits in these sequences. In such a case, in this sequence, the different number of bits are 1, 2, 3, and 4. So the Hamming distance between the iPad and OPAD is 4. And it's such taken that it's most non-regular. What I mean by that is, let's say if we take maximum Hamming distance of 8, in that case, the iPad will be, let's take all zeros, and the OPAD, let's take that as all ones, since the Hamming distance we have decided is 8. Now, you'll notice the different number of different bits between them is 8, hence the Hamming distance is 8. In such a case, you'll notice that the iPad is exactly the complement of the OPAD. What this will mean is when Alice or Bob will compute this first block, which is K XOR iPad, they're computing 0 XOR K, which is K itself. So it does not have any effect whatsoever. And while computing the OPAD, they're computing 1 XOR K, which is K complement. Now, if Eve manages to somehow repeatedly get multiple hashes and analyze the first few sequences of the hash, and if they somehow get the first few sequences of the hash, they get the key K itself. And since they get the key K, they can complement it and get K dash as well. This is even more bizarre when you take the Hamming distance 0. In such a case, you're basically passing K here and K here. So if they can get their hands on the first few sequences of the message itself, they can get their hands on this block, and hence they will be able to pass the second pass and generate an HMAC. This is exactly why the Hamming distance between the iPad and the OPAD is taken such that it's most non-regular. One of the main challenges in symmetric cryptography is the distribution of keys. And to develop an intuition of what we'll be doing next, let's go back to HMACs. Remember this key K? So Alice and Bob will both need to perform these operations at their own ends, and they'll need this key at their ends to perform this operation. So how will Bob know what key Alice used? Well, you could use a key distribution center or a KDC, but again, it all comes down to using a secure channel for transmission and the security of the KDC itself. In the year 1979, Ralph Merkle, Whitman Diffie, and Martin Hillman came up with a way to securely exchange cryptographic keys over publicly insecure channels. Let's see how this is done. So Alice, first, the initiator of this communication, generates three numbers, three constants: a very large prime P, a generator PG, and a private key A. Alice will now compute their public key, which is guided by the formula G raised to A mod P. Alice will now send this P, G, and this public key A over to Bob as per this UML sequence diagram. All right. Notice that Alice did not send A because that's their own private key, that's their secret, and it will only be with Alice. Now, Bob has P, G, and A, so they'll generate a private key or a secret, their own secret, B. Now, Bob will compute the private key, public key, using the formula G raised to B mod P. Bob will now send back this B to Alice. At this point, both Alice and Bob will need to compute what is called a shared secret. And the way that they do this is Alice will compute B raised to A, and Bob will compute A raised to B. Notice that Alice received B from Bob, and A was their own secret itself. So they have all the necessary ingredients they need. Similarly, A was received to Bob from Alice, and they themselves have this secret B. So they have all necessary ingredients to calculate this shared secret S. What this will mean is G raised to B whole raised to A mod P. And Bob will calculate G raised to A whole B whole raised to B mod P. Notice that they have these Alice and Bob have A and B's themselves and not these values. So there's no way that the adversary can tap into A's or B's. They know capital A's and capital B's, which is the public keys respectively. Now what this will mean is you'll notice both Alice and Bob are now generating a shared secret, the same value of G raised to AB mod P. Now both of them have the same key K, or let's call this S, at their ends without even transferring S to the other party. They do not need to do that. So it's secure from any intermission. No one can intercept this. It's secure from interception. Now, remember that Alice and Bob need to compute their own HMACs at their own ends. Alice can simply plug this shared secret over at their end to compute the HMAC. And similarly, Bob will plug in their S computed at their own end to compute HMAC. Now, let's see how to implement these constructs using the standard crypto library provided in Node. One important point to note over here is it's always recommended to use vetted library functions and not create these constructs out of your own for two very specific reasons. One is side channel attacks and the other is bleeding. If you're interested in learning more about side channel attacks and bleeding, I'll provide links in the description. Now, here we are at our repository, and we have set up the TypeScript project. We have installed a few dependencies and developer dependencies. I'll let you know exactly when we come across them. For starters, we will need types node, types express, TypeScript, everything that you'll need, everything that you'll need to get your TypeScript project running. All right, now to get started, let's create a utility function, call it cryptoutils. And we need to import a few things from a few library functions from the crypto library. We'll import them as we need them. So right now what I can think of is we'll need Diffie-Hellman. Yes. All right, cool. Now we'll create an interface over here. And ideally, we should keep this separate from this utility function. But for to create this crisp example, I think it's best if we initialize this interface here itself. This interface holds a key pair that we'll be using throughout this project. And this key pair will contain a few parameters. It will have the key pair, public key, which is of type buffer. It will have the private key, again of type buffer. It will have the generator. We'll see we can keep it either of buffer or of integer. And we'll have the large prime. It's of type buffer. And then we'll have the Diffie-Hellman object itself. Cool. And it's of type Diffie-Hellman. Now, we'll create a function called generate key pair. What that will do is create a Diffie-Hellman object and send back a return the keys that we need. So let's export this function and call it generate key pair. All right, this function is supposed to return a key pair. Now, let's create a Diffie-Hellman object. And in this object, we'll invoke the Diffie-Hellman method. So we'll say create Diffie-Hellman. And we'll have to pass the length of the prime that we need. So a very safe number would be 2048. And then, we'll need to invoke the generate method on this object, the generate keys. What this will do is it will generate the private public key pair for this object, say Alice. And then we'll return the key pair. So we'll return public key, Diffie-Hellman, dot get public key. It's again an inbuilt function that will give you the public key that is used to generate the keys. And we'll return the private key, which will contain, which will give us, will be using generate get private key. So a little fix here. Next, we'll also need to pass the generator. Again, Diffie-Hellman dot get generator. And we'll need to do a similar thing for prime. Let's call this prime. And the function is, you guessed it right, get prime. We'll also need to pass the Diffie-Hellman object. All right. Now, since I want to simulate both the two entities involved in this communication, let's say both inclusive and the account aggregator, I want to create this function that could be utilized by both of these entities, and both of these entities will sit in the same application for this sample application. In this case, just in this case, so we also let's modify this for to be able to use so that this function can be used by both entities. We'll create an optional parameter called prime, and we'll create an optional parameter called generator. Let's pass any data type over here right now. We'll refine this as we move ahead. If you can recollect, if I am Bob and I am provided with these primes, I do not need to generate a fresh key. I do not need to generate a fresh Diffie-Hellman object. What I need to do is, if I'm Bob and I'm given this prime and I'm given this generator, what I need to do is I need to create a Diffie-Hellman object, and I need to provide the prime, the hex for the prime, a special encoding bit. We'll see in a bit the different overrides that this Diffie-Hellman provides. Generator, and then again hex for this generator. All right. At this point, it's a good idea to let's go into the script.d.ts or the file where it's sitting to analyze the different overloads that we can that the script Diffie-Hellman provides to us. So a Diffie-Hellman function has a total of 5 overloads, and the reason why it has 5 overloads is you can provide the create Diffie-Hellman function the prime length, the thing that we did over here. We provided it a prime length. And you'll notice that this also takes an optional parameter of a generator. And we did not give a generator over here. But the catch is, since it's optional, and if you do not provide a generator as a parameter, you can get the generator is by default taken as 2, the value 2. All right. Now, another Diffie-Hellman override says you do not provide the prime length, but you provide the prime itself, and you provide an optional generator. If not provided, of course, it's taken as 2. Well, this is something that comes in handy when you are Bob. Say you've already generated a prime and you've passed the prime to your other party involved in communication. Another override is encodings. Say you provided string. The generator that you provided was not in number, it was in string, and you'll have to provide an encoding that you'll have to convert it to hex. The generator value provider is of hex. Similarly, another override for prime encoding and another override where both prime encoding and generator encoding are present. What we have used over here is an override where we provided the prime, we provided the encoding for this prime, which is hex. This prime is present in hex format, the generator, and the encoding for hex. Cool. We don't need to modify anything else, and this is ready for production. What we need to do now is to define a function called generate secret key, or let's call it shared secret. And the shared secret will take a key pair. It will take a key pair of type key pair, and it will also take a public key. Of type buffer. If you can remember, the shared secret for both parties are calculated as a raised to small a and b raised to small b, which is where the public key comes in picture, the capital A's and the capital B's. All right. Now it returns a type buffer, a buffer object, and we'll return key pair Let's modify this. Let's correct this as key pair the Diffie-Hellman compute secret and compute the secret using the public key. Done. Anyone who invokes any of the parties involved in this communication who invokes this function will be able to generate the secret key, and this will not be transferred over any channels whatsoever. Cool. Now that we have this, it will be great. It will be great if you could create the HMAC here itself. So we'll need another function called create HMAC, and ideally I could have just moved ahead and let auto import do the job, but I need to emphasize that the function that we are wanting to invoke now is create HMAC. Okay, what we need to do is we'll call this function generate HMAC, and this invokes create HMAC, and we'll supply this a data. We'll keep the data type of this data as any for a very simple reason. We want to improve the user experience, right? So we want to improve the developer's experience rather. So a developer who is passing an object, uh, they might be willing to share, they might be wanting to share an object over to Bob, and the object contains some critical information about a user, say a PAN or a social security number and similar things. So I do not want to provide, I want to provide a better user developer experience, and they'll be able to pass any type of data whatsoever. But internally, and we'll see this in a bit, generate HMAC function or the create HMAC functions takes only strings. So internally, we'll convert this to strings, but the developer is free to pass in-depth data. And we'll have to provide this with a secret key. And the secret key could either be of type key object or of type buffer like or binary like. And this type is no rocket science. This type binary like is a union type. I'll show in a bit. This type is, this could be either string or an array buffer view. And both of these have been imported. All right. Now, I'll create an HMAC object and use the function create HMAC. No, create HMAC. And I'll pass in an algorithm. It takes two parameters. The first one is the algorithm that you want to use. Remember, the HMAC is only as secure as the underlying hash that you're using with it. So it takes in two parameters. The first parameter says, what algorithm do you want to use for the underlying hash function? And I say SHA-256 does fine for the use case. And the secret key. Now, update data. This update function will create the digest, and the digest can be extracted using the digest method. And the hex, and the encoding of this digest is of type hex. Cool. We will use JSON stringify. Well, it's important. Well, it will be nice to see that this update function will take type string, buffer, typed array, data view as its type. And in our sample application, we'll convert this data to string using stringify, json.stringify. Now, this utility function is complete. We can close this. Now let's define some controllers. And the very first controller we'll define is for our first entity. We'll call this boost inclusive. Um, boost inc. I'm sorry. And the verification algorithm, verification, the verification controller. Let's import a few things from. We'll use generate key pair, not from the crypto library. We'll use the generate key pair. We'll fix that in a bit. We'll use the generate shared secret. Okay, let's fix this. I want to import from, just so our viewers know, just so you know, I've set up typed alias types, alias path over here, which is why I can use this special construct. I want to import from utils crypto.js, but utils. And as a matter of fact, I do not like this. Cool. Now generate shared secret, generate HMAC, and we'll need the key pair as well because we'll be using this extensively throughout this project. All right. Now, this is Alice in our paradigm. So Alice will have a key pair. Since our Alice is boost, we'll call this boost key pair. And it's of type key pair. And I'll invoke generate key pair function over here. Apologies for that mistake. Now, I'll define a wrapper function over here. I'll create a wrapper function over it that will allow developers to only return those specific keys that they want to actually return. So this is not a very rocket science. This is not a very special function. It's just a wrapper over the functions that we have all created over here right now. So export boost. I'll have to define a function, and I'll call this function shared keys. And this function will define a few values. It will define the public key of boost. We'll call this boost public key of type buffer. And we'll use the boost key pair, and we'll call the public key parameter. Const, again, this time boost private key. At this point, it will be meaningful if I do this. This time we'll be needing private key. Let's change this to private. Another term, we'll need generator, because we need to pass over this generator to our another entity, say Bob, or in this case, the count aggregator or AA. So this time we'll get generator. Again, now we will need the prime. We call this boost prime, and done. And we'll also need to pass. We will not be passing this thing, but we'll need the Diffie-Hellman object. Diffie-Hellman and Diffie. All right. What we'll return is all of these values. We'll return boost, key pair, no, the boost public key, the boost private key, boost generator, boost prime, and the boost Diffie-Hellman. Type Diffie-Hellman is okay. Cool. Now, now we boost will also have a function that calculates their own digest. So we'll have to define a wrapper function over here called HMAC digest that takes in a data, again of type any, and a shared secret keys. The secret key will be of type key object or of type binary like. And the return type of this function could be any. Now, this is where we'll be stringifying our data. So we'll be using generate HMAC. We'll use JSON.stringify and we'll use the data. We'll also have to pass a secret key. Perfect. Now that our verification controller is done, let's create another controller, and this is specifically for simulation purposes. We'll call it aa.controller.js. We'll import again a few things from the crypto library. Let's copy this line and we'll be making a few API requests as well. So we'll be needing Axios. You can go ahead at this point and do npm I Axios. Now, well, let's define a function called that will send the public key of AA to boost. So we'll say export, and we'll have to make a few calls over here. We'll have to make a few net API calls. So we'll make this function async function send AA public key promise. It will return a promise of type buffer. I'll wrap all of these things in a try-catch block. The first thing that we'll do is make an API call to initialize the communication. Since we haven't made our routes yet, we'll revisit this part soon. So after that, let's say once we have made this API call, we'll have a few keys at this point to the account aggregator or the AA. And the AA will have boost's public key of type buffer. And buffer the from response data. Since our response isn't done, our response isn't here yet, uh, it will make sense if we move ahead and at least define the init endpoint. We'll also have to specify the encoding over here. These errors will get fixed over time. But let's go ahead and call it, give it a collective thing, fetch all keys. Another thing that we'll be doing is generate the key pair, generate key pair, and we'll also need to generate a shared secret, right? So generate shared secret. For this, we'll need a variable shared secret. And of course, the shared secret would be of type bar. All right. Before we do anything to this controller, I think it will make much more sense if we go ahead and define a few endpoints in our index.js, index.ts. Cool. So we'll need, of course, we'll need express. We'll need request and response. Response with a capital R. And request with a capital R. From the express package. You can go ahead and just download npmi this express, HMAC digest, and the shared keys. Let's make that better since we use path aliases. I do not want that auto completion. I want alias paths. And this is coming from the verification controllers. Perfect. We'll also need a few things from the crypto library, the crypto utility function that we just created. We'll need the key pair, and we'll need the generate shared secret. Again, we'll go ahead and make that as alias paths. And we'll also need the Diffie-Hellman object from crypto. Besides this, since we are making API calls, we'll be needing Axios. Of course, we can import this as need basis, on a need basis. What we'll do is we'll create app for boost and create an express object. While we are at it, let's create the A app for AA, the express object. And let's also define the port for boost. Let's call this 3000 and port for AA, let's call this 3001. Cool. Now we'll need to store a few things. We'll need the boost public key. Let's recollect everything as per that diagram. We'll need the boost public key. It's of type buffer. We'll need the boost private key. It's of type buffer. We'll need the boost generator. It's a type buffer. And we'll also need the boost prime. It's a type buffer. Are we missing anything? I think we are all done from the boost end. We'll need a shared secret variable called shared secret of type buffer. Whenever we are ready to, whenever this AA controller is ready, we'll also need an AA public key of type buffer. Okay. Besides this, let's also have the Diffie-Hellman object. So the boost key pair of type key pair and the boost Diffie-Hellman object of type Diffie-Hellman. Cool. We'll define a few routes. We'll say app init route is defined on boost, the initiator of this communication. So a GET request, A is supposed to make this request, or Bob is supposed to make this request. Init and a single function that will take in a request and response pair request of type request and response of type response. Perfect. We'll define an arrow function over here. And we'll destructure a few things. We'll need the boost public key. How do we call it public? Let's call it public key, just to make it clear for all of our viewers. We'll call it public key, boost private key, the boost generator, and the boost prime. While we are at it, we'll also have to pass the boost Diffie-Hellman object. And we'll invoke the function shared checkies. Where's checkies? Perfect. Ah, that's fixed. All right. Now we'll send as a response. We'll send back as a response. Let's recollect as per that diagram. What do we need to send? We need to send the boost public key. We need to send the boost generated that Alice decided, and prime that Alice decided. Cool. Now that this is done, let's start. Let's get this start thing. Let's get this running. Listen, and we'll give it port boost the arrow function, and we'll say console log the Boost server is running on port 4 Boost. Cool. We'll need a similar construct for AA's server as well. We'll call it port AA. This is an object of AA, and the AA server is running on port AA. Cool. We are good to go. And at this point, it's a good time to make this API call, the init call. So const response. It's not this response. I do not need this. Response is the name of my variable. Await axios.get. We'll make a get request to HTTP for simulation purposes only. Localhost 3000 / init. Cool. Now we need to fetch all the keys. And by what I mean by all the keys is public key, private key, and the generator. Private key, private use, private. Oh, hang on. We did not send the private key. We we did not send the private key. That's a mistake. It's a glaring mistake. We only sent the generator. And I was wondering why the auto function autocomplete isn't working. So boost generator. Cool. And then we'll need the boost prime. Cool. Now we need to generate the key pair for AA. So const AA of type key pair, and we'll use the function generate key pair. Of course, it will take as parameter this time the boost prime and the boost generator. That's done. We need to compute the shared secret, which is shared secret generate shared secret. And as parameter, we need to pass AA and the boost public key. Perfect. Now that everything's in place, let's return this boost AA's public key. AA.public key. We have wrapped everything in a try catch block. So let's quickly wave a catch block. And for any error, console dot error, an error occurred. Ideally, I should be printing this error, but this is cool for demonstration purposes. And then we'll throw the error. That will do the job. Cool. Now that imagine that recall that same diagram. Alice sent the data, and Bob will need to now verify the data. So we'll need a function. We'll need a function, and let's call this verify data. Again, the data could be of type any, and the HMAC. It takes an HMAC of type string, and the return type, it will necessarily need to be an async function we do not since this will be involved in an API call. So the return type will have to be a promise of type, let's say string. Cool. What we'll do here is we'll define the calculated HMAC or the evaluated HMAC, and use the generate HMAC function over here. And the generate HMAC takes in a data and a secret key. So we need to JSON the stringify the data and the shared secret. And now return if this calculated HMAC is equals to the HMAC that is received from Alice, a boost in this case, we'll say integrity and authenticity. Verified. Remember, HMACs not only provide an integrity check, it also provides an authenticity check, authenticity of origin. And in case it fails, we'll say either the integrity failed or the authenticity failed. And of course, we'll have no way to verify which of these two failed. So compromised. Cool. Our constructs are ready. And at this point, we are ready to write a few more endpoints. Remember the second step. It is to fetch the public key from Bob, or in this case, AA. So let's do that. This endpoint will be hosted on AA's front, and it will be a GET request. Post will make the GET request. And what we'll do is fetch AA public. We'll name it as obvious as possible, just to be sure the developers know. And we'll call this an async function. And we'll need to define a request and a response. Again, some arrow functions. Let's add a semicolon here. And then let's think. We need to first send that public key. So AA dot public key is await, and we'll use the function that we just defined, which was send AA public key from controllers. Let's go ahead and fix a few things over here. I want paths as alias paths and not relative paths. So I'll do this. My bad. Perfect. Now that's ready to go. And now we'll send back there. That's the question. And we'll send back A is public key. A is public key. That's correct. Um, A public key to string and of encoding X. That will do the job. Now we'll need to update this boost key pair. So the public key is boost public key. The private key is boost private key. The generator is boost generator. And the prime is boost prime. And the Diffie-Hellman object is again from boost. So that again, perfect. We are ready to roll. Just a small that we missed out is we need to compute the shared secret as well. The shared secret for, so we'll be using the shared secret method. We'll provide in boosts key pair and we'll also give A is the key, and there we have it. This is complete. Now, let's think at what step are we? We have established the Diffie-Hellman-Merkle protocol, and now we are ready to send the data over to Boost. Let's simulate a data to show that I can actually send any type of data. I will actually create an object. This is my user one, and it has an SSN. And that's a critical piece of information. Remember to always encrypt that. This is only a demonstration on integrity check and not on confidentiality check. All right. Now, app boost will host another endpoint, a GET request, that will fetch the data. So who will be using this? Obviously, Boost will be using this. It's hosted on. It's hosted on Boost, but AA will be using this. All right. So do we need an async function? Yes. And request will be of type request. Response will be of type response with a capital R. Another arrow function. Let's add semicolons over here. And this fetch data will generate the HMAC. And along with the data, we need to transfer the HMAC as well. So generate the HMAC digest, pass in the data, pass in the shared secret. We're good to go. Now, what do we send as response? And if you guessed both the data and the HMAC, you're correct. Data and HMAC. Good. Now that this is done, let's define another endpoint, and this is purely for demonstration purposes. This endpoint will verify that the data is in fact intact. The integrity is in place. So we'll call it verify, and anyone can host it actually. Let AA host this one. AA will be using this one as well. Boost can also check if the sent over data is correct, is accurate. Verify data is an async function, request of type request with a capital R, and response of type response with a capital R. Put those nice semicolons there, and we'll define a response. We call it resp, just to avoid conflict, naming conflicts. And axios.get, do we have the fetch data in place? Yes, so we'll make an HTTP call, an API call to localhost 3000, since it's hosted on 3000. Fetch data. And let's restructure a few things. Let's restructure the data and the HMAC from this response. So response dot resp data. That will work fine. Now, const verified, another variable to say if to use this function, which we call verify data, and we'll pass data, we'll pass HMAC, and we'll send the result of this function. We'll send the result of this variable. Cool. We are ready to test this out. I think our app is complete. Now that our server is running, the Boost server is running on port 3000 and the AA server is running on 3001, we'll head to the Postman client. And the very first thing that we need to test out is fetch AA public key. Note that this init protocol has been implemented inside fetch AA. We made a API call over here, right? So we do not need to do the init call as of now. And simply if we do fetch AA public key, what we'll do is we'll run the init protocol underneath, and as a response, we'll get AA's public key. All right. Now, the next step that we need to do is, let's go to this code and analyze what we need to do next is, we made an API call to fetch data inside verify data, right? So we do not need to do the fetch data over here. Just for information purposes, we want to do that. Let's try, but it's not absolutely required. So fetch is on 3000. And the thing is, I'm getting two, uh, the data object, which contains the name, which is boost user1 and the SSN. Generally, this data will be encrypted and you'll be getting an RSA string or an RSA object. And the HMAC, which is a uniquely generated digest using the SHA-256 underneath algorithm that we decided. And now, if we go over to verify data, remember verify data is hosted on 3001, so remember to change that. We'll see that integrity and authenticity is verified. There should be an and. So we'll see integrity and authenticity is verified. That's working. This is how you can implement Node, the various cryptographic constructs in a Node using the crypto library. And remember, always implement using the standard vetted libraries and do not create these constructs on your own. Do not create Diffie-Hellman on your own, or do not create generate keys on your own for reasons that you might be vulnerable to side channel attacks or hard bleeds. This video synthesizes its materials from a number of sources, the most important of which is Network's Introduction to Cryptography and Network Security by Behrouz Ifarzan. The other is Introductions in Cryptography, which is the original Diffie-Hellman paper published in the year 1976. And the next is the hash function original paper published in the year 1996. I'll provide links to all of these research papers in the description. It'll be a very insightful read.